In this video, we're going to go through a pretty difficult past exam question on particle physics. This is in the new spec, and it was actually in the AQA specification, but it is applicable to every specification actually. So it tells you to identify the number of neutrons in this nucleus here. So I'm going to write this out in case it is a little bit blurry for you. I do apologize for that. I tried to make it as high quality as possible. This number here is what we call the proton number. By definition, it's pretty much just the number of protons. This here is what we call the nucleon number in A-level physics. Nucleon is the total number of protons and neutrons. So if we subtract the nucleon number, well actually the proton number from the nucleon number, what we get is the remainder, which is the number of neutrons. In this case, that's equal to 126, and so option B is the correct answer. Moving on, it tells you a polonium-210 nucleus is formed when a stationary nucleus of bismuth-210 decays. Beta minus particle is emitted in this decay. Outline with reference to beta minus decay, why they have different proton numbers. Well, what is beta minus decay? Is when a neutron turns into a proton, emitting an electron and an antineutrino in the process to conserve energy and momentum, and also lepton number. If you want me to explain that a little bit further, just let me know. Actually, I'll explain it in part D, because I have to. But what's happening here is, let's think about it. 210 here represents the nucleon number. But if a neutron changes into a proton, the total number of protons and neutrons stays the same. However, if the neutron changes into a proton, the proton number increases by 1. Because bismuth decays into polonium, that means that bismuth will have one less proton. So bismuth, let's write this out. It decays into polonium plus the whole beta minus particle, so electron plus antineutrino, meaning the neutron in the bismuth has turned into a proton, which is now turned it into polonium. So what we say is that a neutron changes, I will enlarge this by the way, into a proton, causing the proton number to increase by 1, but the mass number or the nucleon number stays the same. Sorry, I feel like I explained that quite slowly, but yeah, hopefully that makes sense to you guys. Why did it just increase one of them? Let's increase them all to 36. There you go. Moving on then to part D of the question, it tells you explain why an electron antineutrino rather than an electron neutrino is produced in beta minus decay. Well, let's think about this. Neutron into proton plus electron plus this other particle. Why is this other particle an antineutrino and not a neutrino? Well, let's think about lepton number. Only leptons have a lepton number of 1 and antileptons have a lepton number of -1. We also know that for conservation to happen, or for a reaction to happen, lepton number must be conserved. The lepton number of a neutron is 0 because it's not a lepton, it's a baryon. A proton is also a baryon, so it has a lepton number of 0. An electron is a lepton, so it has a lepton number of -1. In order for a lepton number to be balanced on both sides, particle X needs to be an antilepton. On top of that, in terms of charge, if we look at charge, by the way, baryon number needs to also be conserved. These three are always conserved in interactions. Strangeness is only sometimes conserved, so we don't always include it unless it specifies in the question. The charge on a neutron is 0, charge on a proton is 1, charge on an electron is -1, so the charge on this particle has to be 0. In terms of baryon number, for a neutron it's 1, for a proton it's 1 because both of these are baryons. These are, well, this is a lepton, so it has a baryon number of 0, and this also needs to have a baryon number of 0. So by way of this question, we know that it's an antilepton, we know that it has no charge, and we know that it's not a baryon. The only option is an electron antineutrino. If it was an electron neutrino, then the lepton number would be +1. Hopefully that makes sense to you guys. Let's now move on to this, what we call a Feynman diagram. So it tells you an electron antineutrino. I'm just going to enlarge this, so that's this particle here, enters the tank and interacts with a proton. So a proton and an electron antineutrino, how that interaction happens is a proton turns into a neutron and an electron antineutrino turns into this particle here, which is a positron, the antiparticle of an electron. Now, what carries on in the process? Well, the proton has a positive charge which is carried on to the other side of the whole interaction, and that's done by an exchange particle. In this case, because it's the weak interaction, the exchange particle is a W boson. So particle X is a W boson. In terms of Y, we mentioned a proton turns into a neutron, so that'll just be particle Y, a neutron. Moving on to this next part of the question, it says the positron produced slows down and collides with a lepton in a molecule of water. Describe the process that occurs when the positron collides with this lepton. Okay, so straight off the bat, what this looks like is annihilation. What is annihilation? It's when a particle meets its antiparticle and they combine to turn all of their energy into two photons that move off in opposite directions. To show this in a diagram, we have a positron. It will collide with an electron because that's the antiparticle of a positron, and all of their energy will turn into two photons that move off in opposite directions. The reason they move off in opposite directions is if they moved off in the same one, then there'd be more momentum in this side than that side, and momentum won't be conserved in the interaction. So let's write this out in text format. We say a positron meets an electron and annihilation occurs. I will enlarge this, sorry about that. This converts the rest energies of the electron slash positron into two photons. That will get you a second mark. And your third mark is for saying the photons move off in opposite directions to conserve momentum. Perfect. Okay, seems there's a few spelling errors. Sorry about that. I'm very bad at typing, as you can see. There you go. Moving on to this last part of the question, it tells you the range of the electromagnetic interaction is infinite. Okay. The table gives you the range of the strong nuclear interaction and the range of the weak nuclear interaction. So that's 10 to the minus 15, by the way. I'm just going to write this out in case it's too small for you guys. And that's 10 to the minus 18. Describe whether the positron or the electron antineutrino is likely to travel the shorter distance before interacting with one of these fundamental forces. Well, let's compare them. A positron with an electron antineutrino. They're both antileptons. They both have a lepton number of -1. What's the difference between them? Well, this is charged and this is uncharged. We know since they're both leptons, they both experience the weak nuclear force. They both do not experience a strong nuclear force because only hadrons experience a strong nuclear force. What about the electromagnetic force? Well, that only acts on charged particles, meaning it will act on the positron, but it won't act on the antineutrino. So because this is charged, as soon as it enters the field, it will experience the electromagnetic force, whereas the antineutrino won't. It will take a little bit of time, and when it reaches this range here, that's when it experiences a weak nuclear force. So the positron is what will travel the shorter distance before experiencing a force because it has a charge involved. The first mark is for realizing that a positron is charged, whereas an antineutrino, well, let's say electron antineutrino, is uncharged. The second mark is for mentioning that charged particles experience the electromagnetic force. You can skip ahead, by the way, if you want to see the enlarged version of this text. And the third and final mark is for mentioning that the positron experiences this fundamental force, the electromagnetic force, before the antineutrino can experience any force, which would be the weak nuclear force, by the way, that it would experience. The weak nuclear force. Let's now make this larger. And that's everything for this question. Pretty long question and pretty difficult question, but hopefully it made sense to you guys. Hopefully this video helped. If it did, be sure to leave a like. I'd appreciate it, and be sure to subscribe. Thanks for watching. I hope this video helped. If you have any tutoring inquiries, be sure to visit my website www.excellineducation.co.uk. It's on the first link in the description too.